Diffusion is how a gas will move to spread out in a space. In other words, it'll move from areas of higher concentration to areas of lower concentration until it's evenly spread out. Effusion is what we're going to look at here. Effusion is like diffusion, but out of a small pore. This is why a balloon will go flat, because there are small pores in the balloon, and slowly the gas will make its way out of those pores. How fast a gas will effuse depends on a lot of things. The temperature affects it because the particles are moving faster. The pressure, of course, a higher pressure gas will effuse faster. But it also depends on the size of the molecule. And so in this equation, the C takes into account the particular hole and the temperature and the pressure. And it shows just how the effusion rate varies with the molar mass. And what it says is that the larger the molar mass, the slower it will effuse. And you might think that is true for the wrong reason. So what I just said was smaller molecules will effuse faster. And so you might think that that's true because the smaller molecules can fit out the hole more easily. But the thing is, for effusion, we're talking about something that occurs where the pore or the hole is much, much larger than the molecules. And so fitting through, squeezing through the hole is not the issue. So these are not really to scale, but just to kind of show you what we're talking about, how fast those can go through there, what the rate is. And again, it's not about them squeezing through. So why is it that the smaller ones effuse faster? It's because they have a greater velocity. They're moving faster. And why are they moving faster? Well, if they're at the same temperature, they have the same kinetic energy. And the velocity is different depending on their size. So kinetic energy and in this equation, m is the mass of the molecule, v is its velocity, how fast it's going. So if their kinetic energy is the same, because their temperature is the same, then the smaller molecules must be moving faster. And that is true. Let's look at how that works. Okay, when I put the molecules in, the first thing you'll see is diffusion, because they all kind of come out together, but then you'll see them spread out. So let's watch diffusion. I'm going to put in 20 of each. I've got the heavier ones that are blue, and then I'll do the smaller ones that are red. Okay, and I put in 20 of each, and as they diffuse, they're going to spread out uniformly. They are at the same temperature. This is at 300 K, about room temperature. So which ones are moving faster? The smaller ones are moving a lot faster. And that's because of that equation for kinetic energy. If they have the same kinetic energy overall, the smaller ones must be moving faster. Okay, and now I'm going to open a pore, and it's going to look really big, but remember, I don't want the issue being if they can squeeze through. What affects how fast they effuse is their likelihood of bouncing in the right place so that they just keep going. In other words, they're bouncing around randomly, but if they bounce in the right direction, they'll just go out the hole. And so since the red ones are moving faster, they're bouncing more, so they'll have a greater tendency to go out the hole. And actually, before I get started, the particle numbers are over here. And so you can watch the numbers change as I open this. So I'm going to open this. And you can see visually up here, the red ones are going, and there's a difference here in the number. And that's exactly what we said, is that the small ones that are moving faster will effuse faster. So what we're going to do is not calculate rates of effusion, which you can imagine a rate would be amount of gas per amount of time, but we're going to compare the rate of effusion of two different gases. And so the way the math works out is that because it's inversely proportional, these are opposites, so kind of watch for that. A is up here and then down here. And that's because a smaller one effuses faster. If you have a problem that says like A is 5 times faster than B, that means that the fast one goes on top. It means its rate is a bigger number. So if you want to add this over here, like if you say A is 5 times faster, then you'll put a 5 equals to this. One more thing before we work problems. There's a difference between saying that one is faster and one takes longer to effuse. And so for example, I use S for slow and F for fast. If S is slow, let's just say it takes 4 times as long. So 4 times the time required for F. So how many times faster is S? Well, it's not times faster, it's actually slower. So the number here would be 1/4 or 0.25. And it's so the thing is that rate and time are inverse of each other. So I got that as 1/4. So if I say that S effuses 0.25 times as fast as F, that means S is slower. Okay, if it's faster, then my number would be larger. Okay, but I could also say that the fast one effuses 4 times faster than the slow one. So so these go together, that S takes 4 times as long, that means F is 4 times faster.